Yeah, so probably because of free association, I was being reminded yesterday of this old movie called Bringing Up Baby, where baby actually refers to a young pet leopard. And it's always very heartening to come to ICTS because there's this air of boyishness, take that as a gender-neutral term, about the place, which is very gladdening and exciting. So I'll be talking about the geometry of surface representations, and I think I owe a debt of gratitude to Ashok for his extremely lucid introduction to Riemann surfaces. It also essentially says, I mean, I don't have to make a case for what I'm talking about being related to physics. So let's start with the topological classification of surfaces. So these are all closed two-dimensional manifolds, closed orientable surfaces are homomorphic to spheres with G handles. So this was conceived by a bunch of people, Riemann, Mobius, Jordan, Poincaré, Klein, but we had to, I mean, this was done in the mid-19th century, but the formal proof had to wait for the early 20th century by Dane and Heegard. So this G is the genus. And once we have this basic topological construct ready, we start decorating the surface with finer geometric structures to start analyzing finer geometric structures on surfaces. And this is also classical, 19th century certainly. And there are, and it's actually quite interesting that different kinds of geometry come and find this field as a place for interaction. So there's the differential geometric approach, which probably goes back to Gauss, where you're really looking at constant curvature metrics on these surfaces. And it's +1 for genus 0, +1 for genus 0, 0 for genus 1, and -1 for genus higher than that. There's the complex geometric approach, which was elucidated by Ashok yesterday. So these are Riemann surfaces. I'll just briefly say what these are. So these are two manifolds where the transition functions that you are thinking of are complex analytic. There's the algebraic approach, and you look at these same things as solution sets to equations, but you make them compact or closed by not thinking of them as solutions in Cn, but as solution sets in projective space. These three apparently different ways of looking at surfaces, I mean different geometric structures, actually are equivalent, and there's a deep theorem by Poincaré, Koebe, and Klein, which essentially says there's an exact dictionary between the differential geometric, the algebraic, and the complex geometric way of looking at things. The differential geometric way has yet another interpretation. That's what I'll come to on the next slide. So you take, I'll focus on genus greater than 1, that's the generic case. So you look at the model space of constant curvature -1, this is the hyperbolic plane, or the Poincaré disk, that's the stuff on the top. And what you do is you cut out an octagon here, and make sure that the alternate sides are equal. And you cut out this octagon and glue alternate sides together, and you get this true surface. And if the internal angles are all sum up 2 pi, then here you're going to get a smooth metric. And that's how you construct almost by hand a hyperbolic metric on a genus 2 surface. Which essentially means that these pairings of opposite sides, that gives rise to a group of symmetries. So Manjul referred to SL2Z. This is, it's an analog of that. Not necessarily arithmetic, does not necessarily come from Z. But you still get a discrete group of symmetries of the hyperbolic plane, and you can quotient that out to get this genus 2 surface. So this gives you your fourth perspective. The constant curvature -1 metrics on the closed surface S of genus at least 2 these are equivalent to discrete faithful representations of the group of symmetries, which can be identified with the fundamental group of this genus 2 surface, and you have a discrete faithful representation of that into the isometry group of the hyperbolic plane, which turns out to be, and this is one of these wonderful coincidences, perhaps not so much of a coincidence, it's the simple Lie group SL2R quotiented by the scalar matrices plus minus identity. That's this projectivized SL2R group. Okay, so because of this dictionary, which says that whether you're looking at the differential geometry point of view, algebraic point of view, or the complex point of view, you're really talking about the same thing. You can ask about the space of structures, and you can space of such structures on these surfaces, and you can look at it from each of these viewpoints. And that brings us to the next topic. So you're really looking at so that the space has a name. It's called the Teichmuller space or the moduli space, depending on which category you're looking at it from. And from the differential geometric point of view, you're really looking at isometry classes of constant curvature -1 matrix on such surfaces. There's one extra subtlety. You say that two of these metrics are the same if they are isometric, but the isometry has to have a little bit of a marking, topological marking. Basically, the map between the surfaces, which gives you the isometry, has to induce the identity map at the fundamental group level. So that's this extra piece of topological marking. This is the differential geometric way of looking at the space of these structures. If you look at complex geometric or the Riemann surface point of view, you're looking at, you forget the metric, but just look at the complex analytic structure or the conformal structure. So you're looking at conformal or complex analytic isomorphism classes of Riemann surfaces, again, with the topological marking. When you come to the algebraic world, you can't quite, I mean, this piece of extra topological data is a transcendental piece of information. Can't quite put it in, so you just forget it. You're just looking at both projective algebraic curves up to algebraic isomorphism. So that's how moduli space and Teichmuller space appear. But perhaps the neatest way, I mean, well, the biased statement, but one very nice way of looking at these things is from the more representation point of view. What are you looking at? You're looking at discrete faithful representations from the fundamental group of the surface into PSL2R, modulo and equivalence, and that equivalence becomes very simple. It's just a global conjugation of the representation by some element of projectivized SL2R. So these are the 4 points of view on the space of these structures. And now we look at the place where we are embedding all these groups, and that's PSL2R. That is the simplest non-compact simple Lie group. Okay? So this entire thing really starts off where the Lie theory, the smooth group that we are looking at, is the simplest in a very precise sense. So what about the next simplest example? So what's the Lie group that's still a simple Lie group, but not as simple as SL2R? So how about PSL2C? I mean, just take that theory. I mean, this is a natural next Lie group to look at from a number of points of view. It's the complexification of SL2R. It's also, I mean, yeah, it's in a certain ranking, it's just sits after SL2R. So you look at PSL2C from the Lie theory, that's a natural thing. Geometrically also, it's the exact next group that one would be looking at. PSL2C turns out to be the oriented isometry group of the elder brother of hyperbolic plane. It's the isometry group of hyperbolic 3 space. So what are we looking at? If we want to generalize surfaces with geometric structures, we're really looking at then discrete faithful representations of the fundamental group of a surface into PSL2C. Well, now you have to have a topology, which is something that I had conveniently shoved under the rug when I was talking about Teichmuller space. So there's a topology, and the topology is the naivest topology that you can think of. So it's the topology of pointwise convergence. So you think of your fundamental group as a discrete countable set, and you pick any group element from this abstract discrete group pi1s, and you say that a sequence of representations rho n converges to a representation rho infinity if for that little element G, rho n of G converges to rho infinity of G as an element of this matrix group SL2C. If that P bothers you, you can just forget it and you will not lose anything. So this collection of representations equipped with this topology, this is denoted as AH of S. A stands for A, this algebraic topology. H stands for hyperbolic structure. So this would be a naive analog of Teichmuller space in just the next dimension. So how are we going to go about studying these things? What's the geometric study of these representations? So you think of this row of pi1s, just denoted this by gamma. So these are called Kleinian surface groups. They were discovered by Poincaré. So Poincaré. Yeah, anyway, so these guys have a certain property. And so we mathematicians have this rather perverse attitude of worrying about certain wild things which do not happen in nature, whether they could actually happen. And in this particular case, it took a lot of work by a bunch of people, I mean, essentially Thurston and Monahan, to establish that wild, unnatural things don't happen. And so if you take hyperbolic 3 space and you quotient it out by this discrete group gamma, get this 3-dimensional manifold, M. It does not have any wild behavior at infinity. Topologically, it's just the simplest thing that you can think of. It's just a product. If this was H2, you'd just get this S with a hyperbolic structure, as in the previous case. In the 3 dimensions, it's just a topological product, the surface with R. So what does the geometric study of these things become? Let me point out a caveat. If you go up another dimension, 4, it's no longer true. So while things can happen, you'll have to introduce extra hypotheses to remove all that wild stuff. Anyway, so the geometric study of these representations in PSL2C becomes the study of hyperbolic 3 manifolds. So what you're really studying, it's topological, it's surface cross R. Geometrically, there's a parametrization space. So the 3-dimensional analog of Teichmuller theory becomes the study of hyperbolic structures on this topological product, surface cross R, complete hyperbolic structures, where 2 of these guys are called the same if they're isometric. There's a global isometry between the 2. Okay. So now let's just set up a little bit of notation. So what do? You take this 3-manifold M, you have the surface S, equip your S with some auxiliary hyperbolic structure from 2 dimensions. Take a topological embedding, which just takes this M is S cross R, just put S as S cross 0 there, and identify the universal cover of S with H2. So this involves the choice of an auxiliary metric, which is not important, but you just have to make a choice for convenience. And whatever I'm going to be talking about is going to be independent of that choice. So you pick an origin in this universal cover, H2, and the inclusion I lifts the universal cover, the I tilde, from the hyperbolic plane to hyperbolic 3 space, the lift, and denote the image of this base point by capital O, which is the base point in hyperbolic 3 space. So if we try to understand the analog of Teichmuller theory in 3 dimensions, it turns out that new phenomena actually happen. So 3-dimensional hyperbolic structures on this surface cross R, these are broadly of 2 kinds. First, quasi-Fuchsian. Again, Fuchsian groups are essentially the groups in 2 dimensions, H2 mod discrete groups, and these were also discovered by, they were actually discovered by Poincaré and Klein. So they have a bunch of names depending on what perspective you look at them from. These are quasi-Fuchsian groups, or undistorted groups, or convex Gopakumar groups, or QI-embedded groups. What's the point of these? You have this hyperbolic plane sitting inside hyperbolic 3 space. So just think of a crumpled piece of paper. infinite sitting inside this Euclidean 3 space. And then for 2 points on that crumpled piece of paper, you have two distances. One is the shortest distance in Euclidean 3 space, and there's a length of the shortest path lying on that crumpled piece of paper. So you can compare these two distances. So the distances, the intrinsic distance in the hyperbolic plane, denoted d2, and the extrinsic distance in hyperbolic 3 space, denoted d3, they are linearly comparable. Yeah? And at this point, I should advertise this a little bit. It actually makes contact with a problem in an algorithmic problem, which essentially is called the generalized word problem. So the extrinsic geometry versus the intrinsic geometry actually turns out to be related to computability and solutions of word problems in groups. So this is in a certain sense the simplest possible situation where the distances are linearly comparable. What does that mean formally? It means that if you look at your orbit, your point O, act on it by two group elements, G dot O, H dot O, then that distance is more or less up to a linear factor, K, and an additive discrepancy, epsilon. It's essentially related to the distance in 3 dimensions. The right side is written for symmetry. It's always true. So this space, this is what was classically studied till about the 1960s, these representations. And it turns out that QF of S is this collection of representations can be parametrized by 2 copies of Teichmuller space. What do you have really? You have surface cross R. So there's a surface cross minus infinity, there's a surface cross plus infinity. Those guys have conformal structures. And so conformal structures are parameterized by Teichmuller space. So you have a Teichmuller space worth of structures at minus infinity. You have a Teichmuller space worth of structures at plus infinity. And the two together, product of those, exactly parameterize these geometric structures, this collection of representations. This is called Bayes' simultaneous uniformization theorem, proved around the 1960s. So Bayes, back then, conjectured, that these representations, these well-understood representations, is actually dense in the space of all representations. He knew that there were representations which do not belong, which are not in this class. But he conjectured that they are actually dense in the space of all representations. Every point in the representation space has such representations arbitrarily close to it. And this turns out to be true. So the second class of representations are limits of these. And this was called the Bayes density conjecture. It was proven in this decade, for 50 years after Bayes conjectured that. There's an alternate viewpoint that one can take, which is asymptotic. Instead of hyperbolic 3 space, you look at the boundary, which is the Riemann 2 sphere. So the quasi-Fuchsian representations are precisely those for which the inclusion of the hyperbolic plane into the hyperbolic 3 space extends to a continuous embedding from the circle to the sphere. Mind that this is two things. So it's continuous and it's an embedding. So the circle just sits topologically inside the 2 sphere, and that characterizes these quasi-Fuchsian representations. So the circle actually has a Lie theoretic interpretation. It's just SL2R quotiented by the upper triangular matrices. The sphere is SL2C quotiented out by the upper triangular matrices. So what about the other representations, which are then in AH of S, so which are limits of these guys? Do they also give continuous maps? Do they give continuous embeddings? And the answer is that if you remove from this condition the word embedding, then you get exactly these other limiting representations. So you get, for all representations, which are limits, so the asymptotic viewpoint essentially says that the inclusion of the hyperbolic plane into hyperbolic 3 space extends continuously to a map, not necessarily injective, from the circle to the sphere. The first family of these exotic asymptotic maps was discovered by Cannon and Thurston, so these are called Cannon-Thurston maps. Okay, so that brings us to, okay, so we've done the simplest case, the next simplest case. How about other semisimple Lie groups? So other semisimple Lie groups, just think SLNR and SLNC. So what's the generalization of this theory, which started probably in the 19th century, and the SL2C picture started in the mid-20th century and was accomplished essentially in this decade. What about other Lie groups, say SLNR and SLNC? And that theory is a topic of current research. This is what's called higher Teichmuller. And the study was, it's a coincidence. I mean, it came from a very different direction, but the geometric study was initiated in 2005. And these can be studied, representations of pi1s into G, think of G as SLNR or SLNC, can be studied dynamically in terms of this asymptotics. But the right space to look at, as you might have guessed, is SLNR mod upper triangular or SLNC mod upper triangular. So that's called the Borel subgroup, and you look at this compact space, which has a nice geometric interpretation G mod B. In ergodic theory, that's called the Furstenberg boundary. And the dynamical study of these groups on these compact spaces and associated vector bundles give rise to an analog of these Fuchsian and quasi-Fuchsian representations. These are called Anosov representations because of the dynamics. It's motivated by the geodesic flow on surfaces. This was done by Laborie in 2005, and the definition is even to nail it down, it's quite hard. So an alternate approach was given in just last 2 or 3 years by 2 groups of mathematicians, Kapovich, Leib, and Porte, and Guerrero, Guichard, Cassel, and Bienhardt, 2015. And what they say is really setting the whole groundwork. You can think of a representation as Anosov, which is this modification of the interpretation of representations in terms of geodesic flows. You can think of these as quasi-isometric embeddings, but quasi-isometric embeddings, which means that the distances are not distorted too much, with a certain rider. These are quasi-isometrically embedded in a very strong sense. You can also take this asymptotic viewpoint, and they are exactly the ones for which you have an embedding, continuous embedding, from the circle to this analog of the boundary, G mod B. There's a very mild technical condition here, antipodality, which I will not go into. Okay, so essentially Bayes' theory from 1960 has at least a fairly fleshed out version today. What about AH of S? I mean, what other phenomena can happen? Story is completely open, we don't know. And so here is a sample of questions that we have no idea about. What is, how are we going to understand geometrically other representations, even in SL2R, representations which are neither discrete nor faithful? And there is some work of Goldman, but the geometric understanding is still lacking. What about analogs of limits of these quasi-Fuchsian representations? Things which are in the algebraic, I mean, in this Thurston analog of Teichmuller space, AH of S, but not in the quasi-Fuchsian representation. Till date, we don't know any examples outside of dimension 3, really. What if we relax motivated by the existence of Cannon-Thurston maps for arbitrary surface groups, if we relax the continuous embedding circle to G mod B, if we just require a continuous map, maybe call it a higher Cannon-Thurston map, from the circle to G mod B, what do we get? So all these questions are wide open. There is a broad framework, and I'd like to mention this framework because it ties up with where we started. This is the framework of Higgs bundles. The right names to mention here are Hitchin, Simpson, Collett, Donaldson. This was late 80s, early 90s, and it ties up again with physics. In fact, they are called Higgs bundles because of certain similarity with the fields that give the Higgs bosons. And what this establishes is, again, this 3 pronged attack that you can make on these representations. There's an algebraic geometric approach to this, which are vector bundles on Riemann surfaces equipped with certain fields, called the Higgs fields. You have the differential geometric approach to it, which basically says that you look at energy minimizers from the hyperbolic plane into hyperbolic free space, into the symmetric space G mod K. So these are harmonic maps which are equivariant under the action of the surface group. Or you can think of it purely topologically. Just look at the space of representations from pi 1s into G. So these representations are all representations. You throw out some uninteresting ones. And so you can have, again, this interaction between topology, differential geometry, algebraic geometry, and physics to boot. But it will probably require a fair bit of work by mathematicians of different species, maybe mathematical physicists, to even to make some progress towards this. So thank you.
Thank you, Mahan. Questions?
Hi, thanks. Yeah. So yesterday, in fact, you were asking on moduli space, the Riemann surfaces, there's the Weil-Petersen metric.
Yeah.
So in these hyperbolic structures, just in one higher dimension, the one that you mentioned, is it enough to take, since you said it's sort of, at least most of it is essentially two copies of the Teichmuller space, is it some sort of a direct product metric, or is that sufficient? Supposing you wanted to integrate over the space of these hyperbolic structures, what would you sort of do?
Yeah, so the correct place where there is an analog of the Weil-Petersen metric happens to be SLN-R. So C happens to have, the complexification has a different kind of a story. There's not a real nice measure. See, basically what you're doing is you're quotienting out by the mapping class group in order to get moduli space, and you get the volume form there. And that's where you do integration. Whereas here you're really looking at Teichmuller space on both sides, and the natural structure that you get on Teichmuller space is the conformal structure. You don't quite get a metric. On the other hand, if you look at SLN-R representations, this is also this decade work, and it's Labrador, Dick Canary, and a whole bunch of others who have actually established the analog of the Weil-Petersen metric on the space of Anosov representations, SLN-R. SLN-R, not SLN-C. SLN-C is still wide open here.
Understand correct. So, but if you, isn't there a natural notion of trying to integrate on hyperbolic structures for?
There is a metric. There's a symplectic form. There's a volume form. But it's an infinite volume object. See, basically, what happens is that the moduli space is finite volume. It's morally. You can put in a divisor at infinity and it'll be compactified. These guys are bundles over that. So the fibers are. The direction is infinite volume. Yeah. These are very nice. These are all manifolds. Yeah, they're very nice.